I want to take the derivative of this function, but I don't really want to do it just using the quotient rule. Because to use the quotient rule, I'd end up using the product rule multiple times or having to multiply the top out and just to take the derivative of the top, and then for the derivative of the bottom, same thing. I either have to multiply it out or use the product rule. So I want to be sneaky. In my last video, I had a product and quotient of things on the inside of a logarithm, and I was able to use the properties of logarithms to rewrite that as a sum. I was able to expand the logarithm. Well, there's no logarithm here, but I'm going to take the logarithm of both sides. If these two things are equal, y in this expression, then their logarithms have to be equal. So I still have an equation. But what I'm wanting to be able to do now on the right-hand side is rewrite it as the sum or difference of logarithms that are easy to differentiate. This process we're going to go through is called logarithmic differentiation, and at the end of the video, I'll put up the procedure we're using. But I kind of just want to go through it step by step, thinking our way through it before we rush right to the procedure. So now I have the natural log of y is equal to this, and I want to expand the right-hand side. So the natural log of y is equal to the natural log of, and let's see, on the top, I take the natural log of this, but I have two of those because I can pull that out front, plus the natural log of x plus 2, plus 3 times the natural log of x minus 1. And then from the bottom, I have minus the natural log of x squared plus 1, and minus the natural log of x squared minus 9. And if I wanted to be very clever here, I could factor that and write it as two different logarithms. I can actually do the problem either way by noticing that or not, but I always like factoring things out as far as I can. So I'm going to go on and just write that one more step. And so let's see, that will be minus the natural log of x minus 3 and minus the natural log of x plus 3. All right, so now I have the natural log of y is equal to this long expansion of my original logarithm, and I'm going to take the derivative of both sides with respect to x. The derivative of the natural log of y is 1 over y times dy dx, and that's just the chain rule. You can write a y prime there, either way is fine. And so now I just want to go from left to right, differentiating those logarithms. Remembering that the derivative of the derivative of the natural log of u is 1 over u times du dx. So this first one, that's going to be 1 over 2x times 2, and then times the constant 2 out front. So 4 over 2x minus 3 plus 1 over x plus 2. The derivative of the inside is 1, so I'm not even going to bother with that. Same thing here, plus 3 over x minus 1, minus 1 over x squared plus 1 times 2x from the chain rule, minus 1 over x minus 3, minus 1 over x plus 3. Well, I wanted to find y prime, and I'm almost there. I wanted to find dy dx. I wanted to differentiate. So now all I have to do is multiply both sides by y. And so I think I'll move that to the next board. So let's see, y prime or dy dx would be y times all that stuff I just wrote down. Minus 2x over x squared plus 1, minus 1 over x minus 3, minus 1 over x plus 3. And I found dy dx. And if this was an implicit differentiation problem, I'd leave it there and be done. But I realized that whoever wrote this problem probably wants an answer in terms of the variable x. So I have to come back through here and do one more thing. Where that y is, I'm going to write down the original function y. And it takes just a second for these ugly functions. Sometimes it's a bit annoying, but that's okay. Just copying an answer over. And now times all of this stuff. And it's not the best looking derivative in the world, but we've differentiated. And in a problem like this, if it says find the derivative, just write it down just as I'm doing here, and only worry about simplifying it if it tells you to. So I found my derivative. I'm glad I didn't have to use the quotient rule a whole bunch, and I'm done.